Hey folks, the next couple of videos are going to focus squarely on security. And this is something I've been really excited about doing because it's an area that I'm very interested in. I think that it's important for every developer to consider because, man, like most of the hacks out there are just because a developer was lazy and they left some vulnerability in there that they should have known about. I really enjoy that process of thinking about how your code is vulnerable to attack. And it's called game theory, right? Where you're thinking about what your opponent's possible moves could be, and then you try to, figure out what you can do about it. And when you design with that in mind, you design really solid code. And I have a lot of experience in this realm because I've been doing websites and managing websites and stuff like that since the 90s, and I've never been hacked. Like none of the servers, none of my personal computers. I haven't even been defaced. Like no hacks have ever actually gotten through, and that's not for lack of trying. Here's a report from the 12th of June, so just last week. Somebody came by Discord and was hitting it hard. They were hitting my login with just a whole bunch of random stuff and really fast. We're using some sort of tool that's doing this for them, and they're like trying to do weird SQL injects just all over the place, and they didn't get through. Like 120 attacks per minute, and they didn't get through. I'm not claiming to be some sort of security expert. It's just. And seriously, like if you're a hacker that's watching this, do not take this as a challenge. I'm not a security expert. I'm just an enthusiastic amateur because I really do enjoy this stuff and I like thinking about this whole process. Like I have fun with it. Like if you were to go to Discord and you were to try to log in as me, you would get banned instantly. Like it would just immediately ban your IP and anything that's ever been associated with your IP. If you try to put my name in here or anything that you might think would be useful, like admin or god or anything like that, if you try any of that into the main login panel, you're just instantly banned because that's not how you log into my website as an admin. And even if I would show you that, but it's just a pain in the ass to unban myself. I made that also tricky. To unban an admin is a 3-stage process. Like anybody who does get admin credentials now has to deal with a 3-stage process to unban. And if you screw up at any one of those points, it resets on all the others. So you got to be very careful when you're trying to unban yourself, and it's just a massive pain in the ass. But if you do manage to get in and you're in my control panel and stuff, there are booby traps all over that, which is why I know it's a pain in the ass to unban myself, because I've accidentally hit some of those booby traps when I'm on the site early in the morning before my coffee's kicked in. Like, it's fun to just think about these things and then add booby traps to your code, because why not? Even if you might hit them yourself, it's still fun and engaging in the process. So for these examples, we're going to be using the peer-to-peer network that we've been building up in this intermediate Python series. You don't have to have seen any of this because I'm going to try to make these two kind of standalone, just focusing squarely on security, but we are going to be using the practical example here of this peer-to-peer network that we've created, because peer-to-peer networks provide a really interesting security playground for us to think about. Because in normal relationships on the internet, we have a server client, and the server can do something to indicate that it's the server we're looking for. Like when you go to an HTTPS site, that S means that we have a certificate saying that you're at Facebook and not Fakebook or whatever. That whole authentication process is dependent on being able to verify who you're connecting to. And in a peer-to-peer network, you don't have that kind of verification. There's just no way of knowing who can you trust. And in the way that we've structured this, our app is just going to run around through our local network and try to hit every single IP it can on the port that it's looking for, which is 11111. And if it hits something there, it needs to now figure out, okay, is this somebody I can trust? Because if it's not, if you just start sending your password at this thing that happened to respond on that port, well, now you just gave away your password. If there was a compromised machine in your network, your scale that tweets or whatever, any Internet of Things is definitely a vulnerable point in your house and your home network. So like obviously nobody's going to actually be trying to do this, like trying to hack you for whatever reason, unless you're a high value target. But it's good to think about these things. Like, how do we actually authenticate and say that, no, you can trust me, you can give me the password so we can, make the handshake and say that we both trust each other. But who's going to do that? Because if the server is just giving you the password, then what the hell's the point of that? Because then the attacker just comes around as a client and he gets the password. So how do we make it known that we can trust each other? And the way that we're going to do that is complicated. And if you do have any security experience, you might be looking at the way that I start this, and you're going to be angry at me because you're saying, oh no, that's the wrong way to do it. I'm going to show you how this is the right way to do this. Okay. So we've got this current, so this is all peer-to-peer. We've got the login and the welcome, which is the recipient of the login, all in one package here. And in that welcome portion, we're challenging right now. We're just giving a nonsense string. We're going to create a real challenge string that's going to identify ourselves to the client and say, hey, we are actually who you're looking for. So we're going to need to make a challenge encoder, which is... So the first concept that we need to get across in this is that math is the answer, okay? We need to figure out some sort of mathematical way to prove things. So we need to think about what data points are shared and known between these two machines so that we can figure out if they're both doing the same math together. So one of the things that we do know for sure is our IP, and our client will know what our IP is as well. Now I'll say server and client just to indicate that the client is the one connecting, even though this is peer-to-peer. So let's take our IP and make that a number we can use mathematically. So the IP is a string. So I'm going to do a list comprehension here, where I'm going to break it apart. So for I in my IP, I'm just going to split that on the period. So now it's going to give us 4 slices, and those are all going to be turned into integers. And now we can sum that by simply saying sum and passing in this IP list. And now this gives us the total of all the numbers in our IP combined mathematically. We can now use that to do something else interesting. So for this next trick, I'm going to need to import string, and I know I'm going to need date time as well, so I'll grab that while I'm here. And what I'm going to be doing now is making a list of possible characters that we can use to generate a random string with. So the possible characters are just going to be the entire alphabet and numbers. And I'm going to use string ASCII lowercase, and I'm going to add to that all the characters that are in a string ASCII uppercase, and then string digits. So now all of those digits and everything have been combined into this characters thing. Let me show you what all this is doing. Let me bring up Python console. My import string, import datetime, my IP, just say 192.168.1.1, and paste in all that we just wrote. So now the IP sum, when you take the IP 192.168.1.1 and just add those numbers together, you get 362. And you see characters is just this big string of all of the possible characters in the English alphabet, along with 0 through 9. So now we've got this. Oh shit, I should have imported random while I was at it. This is now something we can randomly grab characters from. So let's do another list comprehension to create a scramble of characters. So we're going to call this a scramble, and it's going to be a list that I'm going to join. So random choice of characters for, and I'm just doing an underscore here because we're not going to use this variable, range in IP sum. So I'm saying, in range. So I'm saying from 0 to whatever our IP adds up to, pick a random character. So you can do that over and over and over again until you reach that total number of IP sum. And it's going to create a whole big scramble of things. So let's see what that looks like. Oh. So we got this huge scramble of things that is 362 characters long. Now, another thing that both the client and the server will know about is whatever the current time is. So let's use the hour that it is right now. So let's take datetime, UTC. Try to use UTC now whenever you're doing anything like this, because you don't have to worry about different servers being on different time zones or anything like that. Everything is using UTC. So We want to get the string from time and the hour. Now we could put this hour at the end of the scramble by simply doing, challenge is going to be equal to scramble and hour. So if we return this challenge now, and our client and server are communicating through little JSON packets, it'll get this challenge and it'll say, well, in fact, let me write the decode right now, just so you can see what I'm talking about. And we're going to need the challenge. And this is going to return a Boolean. If we take this in, we can do the same math that we did up here in the challenge to find where the hour is in this scrambled nonsense. Because, remember, we're getting this crazy ass big thing here, and we can stick the hour into that. And it's only at the end. Like, obviously, this is a very simplified example. Usually you'd have like a second layer of scramble over here. But we're not doing that for just keeping this video moving. This is going to be a long video as it is. So we can now say that the hour is what we're looking for. This is some verifiable information. If we do the math the way that this guy did the math, we should find the hour. So let's get the IP list of our, do basically the same thing here, except instead of looking at our IP, we're going to look at the connected remote host address, which in this case, since we're using WebSocket, we can just do this remote address, and that's a tuple. By using the 0 here, we're getting the first item of that tuple, which is the IP. So we're going to now be able to split that the same way that we were splitting our own IP, and do the same thing where we now get a list here, which we can just sum, and we now know how much garbage is in this challenge file. We know exactly how long the scramble is. So we can say, even if there was some other thing at the end of this, like, in fact, I just caught myself before I started bouncing around. I got a real bad habit of doing that. So I want to show you all this stuff at once, and I got to take my time here. So we can get the exact location of the hour. Even if there was other stuff at the end of this, we would know exactly where to find the hour, because we know that the scramble is this long. It's whatever this adds up to, it's that long. This is all nonsense. This is what we want. So we can say hour equals challenge, and here we can project into the string of a challenge as a list. Like here, this is a string. We can do what look like array or a list type indexing here, where we do this colon and then a number. In this case, that gives me the first 4. And if I move the colon to the other side of that, it's going to skip the first 4 and just give me everything after that. So in this case, we want to do that here, where we're doing we're going to do the IP sum and then the colon. And now we're going to skip past that whole big scrambled nonsense and just have the hour. Now we can just check, is the hour that we've arrived at mathematically doing all this nonsense, skipping over the nonsense and getting to this, is this equal to the actual time that it is right now? So big time, etc now, string from time, and return true or return false. So this should all work. We could test this, but I want to show you how people go wrong with this. Okay, so like, this isn't actual security at all. This is just nonsense that we've been putting together mathematically. But as soon as, like, I mean, this honestly wouldn't take a lot to figure out. You could try to get clever with this, and I've seen people try to do this, where we're going to say, like, okay, this looks like some big convoluted scramble of string. It kind of looks like it might be base 64. Like if we do base 64 encode of a string. Oh, gotta encode that. See, it kind of looks like the same thing, but you notice how it's got these two equal signs at the end of that? If you ever see equal signs at the end of a string, it's probably base 64 encoded, because that's a common way to encode data that's being transmitted across the internet. So we could fake it by making our challenge nonsense here look like it's base 64, so that if an attacker gets that, he can grab this and he's just like, well, it doesn't decode as base 64. What is this? He's going to confuse him, right? So let's figure out how we would do that. We need to make sure that whatever our challenge equals, it needs to be a length that's divisible by 3. Like every base 64 thing has to be divisible by 3, and if it's not, it pads out the missing spaces with these equal signs. So our mod will be equal to the length of challenge. So 3 minus, yeah. And if mod, if this is 0, this would be 3. So if mod does not equal 3, then we want to add however many, oh, whoops. I missed the modulo there. All right, we got to actually get the module of 3. And modulo is when you divide something and you get the remainder. It's the remainder of dividing this number by 3. Like length of a string is 16, and 16 divided by 3 equals 5.33. But if we do a modulo here, it gives us our remainder of 1. So we're saying, what's the remainder minus that remainder from 3? That is how much we need to pad this thing by. So we'll do our padding equals, this is a cute trick that you can do in Python. I'm saying our padding equals this, and we're going to multiply that by mod. So if mod is 0, then you get no equal signs. If it's 1, you get 1. If it's 2, you get 2. And you should never get 3, because there would never be 3 in a base 64 thing. So we just tack that onto the challenge. Padding. Just pop that up there. All right. So now we've been really clever, right? Like now we're obfuscating our nonsense here, where we're scrambling things. Is that security? It's still not security. This is just more nonsense that we've added. Like now we gotta try to, subtract any equal signs from this thing. We've just made our lives more complicated. We haven't actually added any real security to this. This is security theater. It's security through obscurity, and that's not security at all. It's often very useful to include the obscurity. Like I was saying, like you can't go to the actual login page. You don't know what the actual login page is to log in as an admin on any of my sites. So some obscurity is helpful, but don't rely on that as your security. We need real security here and not this nonsense. But we can use all this nonsense in a very novel way to create that actual security. So a good rule of thumb is never do any of the actual security math yourself. If you think that you're doing it wrong, right? Real mathematicians need to be involved in the process of encryption and things like that, because any failure in your math will be exploited. Okay, so rely on the professionals to do that. And there are just a ton of different modules in Python that will do the math for you and do it securely. My favorite is from the Werkzeug package, which is made by the guy who does Flask. And this is like really battle tested. It's got this great security submodule in it that we're going to grab check password and generate password hash. And this is going to take our password and hash it. But we can't just rely on doing that alone here, because if we take our password and whatever it is, say it's password, we generate a hash with it. Let me show you. Copy and paste that whole line. And we generate a password hash password. Okay, that gives us this. Now, if we were to just pass this to anybody who might be whoever's answering on port 11111, then we've just given them a password hash that they could turn around and now connect to us because it's peer-to-peer, right? So we just gave them the tool to fuck us up. It's like, we don't want to do that. We need to somehow include other information in here that we can mathematically derive that's going to be additional to this hash. Because if you add other things, you get an entirely different hash. So we need to do some sort of mathy thing here to get the stuff that we're adding to this. And it's okay to do the math for this part. And we've already done all that math. That's what all this has been about. We've now got this thing where we know exactly how long this scramble should be. And that's just a whole bunch of nonsense that we've added to create this hash, right? So we can now add this scramble itself to our password and create a really big hash that isn't going to be particularly easily deducible. Because right now, like this, it might look like this is secure. It isn't though, because as soon as you post this on the internet, like in GitHub or something, somebody can look on your source code and say, well, this is just some dumb, I can do this. This is no problem. This is not a security challenge. Now they would have to have your password in addition to all of the other nonsense that we're doing. So this is where the real security comes in. We're going to actually generate a password hash that's going to be the scramble, not the challenge, not the full challenge. We just want the scramble. And then our real password, in this case, is stored in our app's settings. And I mean, now we could throw in other things like, instead of the hour, let's get the timestamp to make this have a element to it that is time expiring. So we'll get that date time UTC now timestamp, and we pop that in here. And now we need to make sure that the recipient, because right now he's only getting this challenge thing, and he knows how to get the scramble out of that, but he also needs to make sure that he knows the timestamp when we assign this. So we can now return the pass hash, and we need to also make sure that we're returning the timestamp so that when we're at this welcome stage here, so at this stage, we need to be communicating all this important information to our potential client. So here we'll put in the challenge as that goofy not base 64 thing. The actual pass hash, we can do an extra layer of obscurity here and like call this an API key or something instead of like explicitly saying this is the password hash. Like this is what we got for our API key, and the timestamp shouldn't seem particularly odd. Like maybe there's just something in there, like his host name. Like that's not relevant information to a hacker, but it is actually relevant information because they're going to need it for the decoding process. So let's go and make the decoding process make use of all that. So here we'll say that we are expecting a timestamp, the challenge, and the pass hash. And now, instead of worrying about the hour, we want to do the reverse of this, where we grab that whole big nonsense. So instead of skipping all the nonsense, we want to grab the nonsense and call that our scramble. And we know all the other information here, so now we can just return what is the result of doing a check password hash. And here we put the pass hash first, and then we reconstruct this whole thing that we used to hash with. So here we'll do scramble, and we'll do our password, and the timestamp that was provided to us. And this will return a true or a false, whether or not we have actually provided the correct information. So let's now make sure that our login is using all that information. So we get this challenge, and we're checking, make sure that it's not doing any kind of buffer overflow on us. Let's make this just a little bit bigger, because that could actually be a bit bigger. So now we need to actually verify that this challenge is good before we move on to giving it our password. So let's use now our self challenge decode, and here we grab all that information from the challenge document. Because remember, this is a JSON file. It's addressable as a Python dictionary. So we just go get the challenge timestamp and the challenge and the challenge API key. Oh, shit. I'm not awaiting these things. Shit. If await. Okay, actually, we want to say if not await. If this fails, then just return. Like, whoever just sent us this challenge thing was not legitimate. He wasn't really the guy we were looking for at all. So he either failed to hack us, or it was something else altogether. So let me make sure I'm awaiting, or I need to be awaiting things. Like, I didn't know that I just screwed that up in the welcome challenge encode. The welcome. Yeah, we need to await this. All right, let's see if there's anything else I need to change here. So yeah, if it gets to this point, then we can actually say, well, okay, this is definitely a machine that's running the same code base as we are, so we probably want to actually exchange passwords with them. For this video, we're going to just give the password in plain text. In the next video, we're going to do real encryption and stuff for all of our messaging. So just give them the password as plain text for now. And we'll send that. And over here, we'll check if the password matches. And all right, that looks good. And this doesn't need to return anything, but if we don't get an authorized message back, let us know that password mismatch on this host. We probably want to do something if this fails, like just to let us know that we got some kind of weird challenge. So invalid or malicious challenge from this hostname. This should all work. God, I hope I'm not screwing something up. Let's fire it up and see. All right. Server started without any errors. Let's load the client. Remember, they're all part of the same class. I'm just breaking them apart, and I got to change this. Another part of security is operational security. And in this case, I keep changing my IP, my internal IP, because I'm showing videos with my IP. And that would be a problem if anybody did actually want to come attack me. So I need to keep changing where this is scanning at as I keep releasing videos. So let's try this again now. So it's scanning at a different range. And it should connect now. Connect to Thoth. No errors. Let's see if they get the status. Yes! Client set status. Okay, so I know that feels anticlimactic because it looks like, well, they just did some things, but they did things through all of our nonsense that we've been working on in this video. Like, I didn't hit any errors. I'm kind of amazed that I got this in this... I'm really actually pleased with myself right now. They are working. They're doing all of that nonsense. They're doing the same math to figure out which nonsense is relevant nonsense. And it's all allowed them to make this secure handshake here to establish the connection. I'm going to cut this video right now. We'll get into the encryption for all the other stuff in the next video. I'm up to 3 patrons. Thank you very much to all 3 of my patrons for their support. Take it easy, folks.